All right, so this is the first of two lectures on Chapter 9, the gaseous state for this Chem 100 course. And so in this first video, our primary look is going to be at some of the relationships that exist between some of the different ways that we can describe gases. In the second video, which will be an in-person lecture, we will talk about some of the calculations that we can do with those gas laws and some of the things that we can find out quantitatively about gases. So we start off today from the qualitative standpoint and defining our properties of gases. And these properties should be relatively familiar to us already. After all, we've talked extensively about what gases are and what the differences between the phases of matter are. So this shouldn't be too much of a new thing for us, but just as a review, the properties of a gas include that it has neither a definite shape nor a definite volume. The gases are so far apart from each other from a molecular standpoint that they will just uniformly fill whatever object that they are placed into. So put them into a cup, they fill up the cup. Put them into a room, they fill up the room. Put them into the outside, and they will fill up the entire atmosphere. And so because of this, we know that it will uniformly fill any container that we put it into. We also know that when that container is closed, as is the case in this container is closed, the gases inside of this container are exerting a pressure on this container because as they are moving around inside of this coffee cup, they are bumping into the walls of the coffee cup and exerting a force on that coffee cup. And that force is what we call pressure. We also know from our own experiences that volume can change with temperature and pressure. Probably the most common example of this is look at your car. Your tires on your car will change in pressure based on temperature. And if we have enough of a difference, we'll actually see that the tire will deflate or inflate based upon temperature conditions and based on pressure conditions as well. I put more air into the tire, it inflates more. I take air out of the tire, it starts to contract. I drive on a hot day, it expands. I drive on a cold day, it contracts. So all of those things are things that we know about gases. Well, we also know they mix completely with other gases. So if I put two different gases into a container with each other, eventually they will kind of all mix up together with each other. There is no, polarity kind of considerations because the gas molecules are so far apart. And that is also why they are considerably less dense than liquids and solids are. The molecules aren't touching each other. There's a lot of empty space between them. And so their density is going to be considerably less as a result. And so I want to actually jump ahead. Your book goes into a different direction. I want to actually get into the theoretical constructs of gases first, because I think if we can understand theoretically what a gas does, why it behaves the way that it does, it'll go a lot more toward helping us to understand the qualitative relationships between those variables that I just mentioned: pressure, temperature, volume, amount of gas, and so on. And the theory that we use for this is something called the kinetic molecular theory of gases, KMT. What this KMT does is it assumes 5 things about a gas. First thing it assumes is that the gas molecules themselves are tiny compared to the overall volume of their container. And that should make sense, right? If we have a gas molecule and the size of that molecule is on the micrometer or nanometer kind of scale, and we've got this big container that is measured on the cubic liter scale, then we can pretty much assume that the volume of that gas is not going to be very significant compared to the volume of the overall container. Number two, we assume that they do not interact with each other. This is a space thing. We have great distances between the molecules themselves. We can really only get attractions and interactions between molecules when they are close together. So if they're not close together, they're not going to interact with each other. We know that gas molecules are spaced out from each other. So the likelihood of them interacting with each other, of them attracting each other, is pretty low. We know that they are in constant and random motion. Well, all molecules are. Solids and liquids are as well, but because of how close they are to each other, they tend not to move nearly as much. Gases, because there's so much empty space in between, they can fill up and move all around their containers. When they interact with each other, they engage in what are called elastic collisions. All that means is that the energy of the collision is conserved, and so the amount of energy that the two molecules come in with equals the total amount of energy that they leave with. We're going to assume that these interactions do not generate heat, they do not generate light, there is no energy loss from them, that they are indeed elastic collisions in that regard. And so that means that gases are going to have a constant pressure within their container, because as they collide with their container, they're going to exert a certain amount of force. And that amount of force is not going to slow the gas molecule down in any kind of way. And that same thing is going to happen when they interact with each other. And then finally, we assume that they have an absolute kinetic energy, rather an average kinetic energy. On average, their kinetic energy is the same if they are at a constant temperature, and it's proportional to that absolute temperature. So with absolute temperature there, the key word here is absolute. And when we see the word absolute, our brains need to go to, these are temperatures in Kelvin. So we're talking in particular here about a Kelvin temperature as opposed to Celsius or Fahrenheit. Important distinction to make once we get into more of the quantitative aspects, because a 10-degree difference in the Celsius scale and a 10-degree difference in the Kelvin scale, while the same difference from a temperature standpoint, when we multiply and divide, much different in terms of their overall impact into the multiplication. So that's the kinetic molecular theory. This is the theory that we are going to come back to often to describe and how gas interacts with other gases, or how gas pressure, temperature, volume all impact each other overall. Now, before we get to that, there is another concept that we want to tackle, and it's the concept of something called diffusion and effusion. Now, these both describe gas behavior in terms of the flow and the movement of gas particles. And so effusion is the flow of a gas through a small hole of a container. So let's imagine for a second here that I've got a balloon, and in that balloon, I take a little tiny pin and I poke through that balloon right there. Effusion would be the gas going from inside of this balloon to outside of the balloon through that hole. Now that's different from diffusion. You've probably heard of diffusion, especially if you've taken any kind of a biology class. Diffusion is used for describing the movement of particles from an area of high concentration to low concentration in biology and other kinds of applications. What we're talking about here specifically with gases is the spread of a gas from an area of high concentration where it's released to all parts of the room that it exists in. And so the analogy I like to give for this is, let's just imagine for a second that you're going home and whoever's at home, your mom or your dad or your, someone from your family or, whoever, your roommate has just made cookies. They've just come out of the oven. And immediately you walk in the front door and that's what you smell. And the reason why you smell that is because those cookies, which are on a plate, having just come out of the oven, have an odor. They smell like something. And that odor starts here at the cookies, but eventually it's going to start to move its way out from the cookies to the other parts of the house. And it's going to go to whatever spot, wherever it is possible, that particular aroma, whatever that molecule is that gives cookies their great smell, whatever that is, that odor, that gas, that vaporized substance makes its way throughout the rest of the house. And so that's diffusion. So effusion is the movement of a gas through a small hole. Diffusion is the movement of a gas through space. And both of these can be described and defined using something called Graham's law. What Graham's law states is that the rate of diffusion, or effusion, is inversely related to the molar mass of the gas that we are studying. Now, there are some equations for this. We're not going to get into the equations. We're not going to try to calculate how fast one gas moves versus another. What we need to know is the qualitative relationship here. And the qualitative relationship is slow gases come from heavy molecules. Fast gases come from light molecules. So if I compare the molar masses of a pair of gases to each other, I should be able to compare and quantify which gas is going to diffuse or effuse more quickly. So as an example of that, let's compare these four gases and let's rank them according to their increasing rate of diffusion. So that means slowest first, and taking it all the way to fastest. So I've got helium, krypton, nitrogen monoxide, and oxygen. All I need to do for each of these is determine the molar mass of all of them and then put them in the appropriate ranking order. So I've got helium, I've got krypton, I've got nitrogen monoxide, I've got oxygen. So for their molar masses, I'm going to need a periodic table. So my periodic table here on my textbook says that the molar mass of helium is 4.00 grams per mole. That the molar mass of krypton is 83.80 grams per mole. Nitrogen monoxide, I need nitrogen plus oxygen. So nitrogen is 14.01, oxygen is 16, so this would be 30.01 grams per mole. And then finally oxygen. Oxygen is 16 for each oxygen atom. There are two. 2 times 16, 32.00 grams per mole. So those are my four gases. If I'm putting them in increasing order, I would start with the slowest, and the slowest would be the heaviest. So that means that I'm going to start with my krypton. Then my next heaviest would be oxygen. So oxygen's a little bit faster than krypton. Nitrogen monoxide, NO, is a little bit faster than oxygen. And then finally helium is the fastest of them all. And so that's all I would have to do. Take the 4, take however many it is, find their molar masses using the periodic table, and then just rank them accordingly. If it's increasing rate of diffusion or effusion, then we would put the lightest on the last and the heaviest on the first. If it was decreasing rate, well, then we'd start with the fastest and end with the slowest. We come now to describing gas behavior. And again, we're going to link all of this back to that kinetic molecular theory. So there are 4 primary ways that we can describe a gas, other than by its chemical formula. If we're talking about just its kind of physical properties, things that we can measure its pressure, we can measure its volume, we can measure its temperature, we can measure how much gas we have, number of moles of gas. Those are the 4 parameters. And each of them are impacting the others. Let's talk about pressure first. Again, pressure is the force that is exerted by a gas on an object. Again, this comes from the movement of those gases, the collisions between the gas molecules inside of the container and running into the container itself. And when those collisions occur, those collisions exert a force on the object. We call that force a pressure. Right now, you have pressure being exerted on you. Atmospheric pressure, that is the pressure of the gases in the atmosphere that are being exerted by the fact that we are on planet Earth and the gravity provides a force on which those interactions between us and the gases can be applied. So when the gas molecules interact with us and collide with us, they exert a small amount of pressure on us. They exert a small amount of pressure on everything that they encounter. Now, in terms of pressure units, there's a good chance that you are probably unfamiliar with most of the ones on this slide. For the international system, the correct unit of pressure based on base units is the Newton per square meter. The Newton per square meter is something that is referred to as the Pascal. Pascals, PA, are the SI unit for pressure. Now, pascals are tiny amounts of force. And just for context there, a standard atmosphere of pressure, that is the pressure that is being exerted on you right now, is about 101,325 pascals. So from that standpoint, pascals are not terribly useful to us. If we see pascals, we will see them in their kilo form, which would be kilopascals. 1 kilopascal is 1,000 pascals. That tends to be the direction that it goes. Again, we don't see those terribly often either. We are more likely to see, at least here in the United States, measurements that are barometric, which would involve things close to, but not the same as this unit right here. Millimeters of mercury is the metric barometric conversion unit. Sometimes that barometric conversion unit is referred to as the torr or the torricelli, and that's named after the guy who invented the barometer, Evangelista Torricelli. Here in the United States, our pressure units tend to focus mostly on weather, and we think of it more as inches of mercury, or INHG, or pounds per square inch, which we know better as PSI. And there are relationships between these units that you're looking at now and these ones that we see more commonly here. In fact, we can look at those right here, right now. So a standard atmosphere of pressure is 1 atm, 1 atmosphere. That is equal to 101,325 pascals, 101.325 kilopascals, 760 millimeters of mercury, or again, torr, 1.01 bars, And notice the relationship here between bars and pascals. It's another way of looking at things. Or probably more consistently and more importantly to us, these two at the bottom, 1 atmosphere is about 14.7 psi, and 1 atmosphere is about 29.92 inches of mercury. So when you look at those weather forecasts and they say that, you know, the atmospheric pressure today is 28.85 inches of mercury, you can contextualize that as, okay, that's a little bit below an atmosphere of pressure. And so if it's a little bit below 1 atmosphere, is it because we are just having a low pressure system kind of day, where that could mean that maybe it's going to start raining, because precipitation and low pressure do seem to have a positive correlation with each other? Or are we talking about something like, well, we're just a little bit above sea level, and so 1 atmosphere of pressure is really, you know, measured at sea level, and so us being a little bit above sea level would drop the pressure just a little bit. But that is the relationship between all of those units. Now let's go back to that previous slide, because it does cover the idea of the barometer. In the barometer, we are talking about how do we measure atmospheric pressure. And the way that this works is we have an open pool of mercury. And so the mercury has 2 forces being exerted on it at the same time. Since it's open to the atmosphere, we've got the pressure of the atmosphere pushing down on that mercury. And as it pushes down on that mercury, it'll start to push mercury up the column, very similarly to what you saw in lab with the gas laws experiment, where the pressure of the gas inside of the flask pushed the water up the piece of tubing. Now, contradicting that particular force, we've got gravity. Gravity is pulling everything down toward the center of the earth. And so gravity is pushing down on that mercury column while the atmospheric pressure is pushing it up. And so eventually what we come to is, we come to a point where the pressure that is being exerted by the atmosphere is equal to the amount of pressure, the amount of force that is being exerted by the force of gravity, and it stops. We stop going up the tube, it levels off, and that's where we measure how much mercury is in the tube. That's why we measure it in terms of inches of mercury or millimeters of mercury. And so again, this is accredited to Evangelista Torricelli, the inventor of the barometer. And that's why, again, millimeters of mercury are sometimes referred to as torr, because as kind of a tip of the hat to that particular scientist who did that discovery. Let's go ahead and do some calculations of conversion just as practice here. Now, one of the things about this particular table is that since all of these values are relative to 1 atmosphere, the transitive property of mathematics still applies, which means if they're all equal to 1 atmosphere, that means that they're all equal to each other as well, which means that in this case, 760 millimeters of mercury is equal to 29.92 inches of mercury. I don't have to go and look for the conversion. I've got one right here. So for this conversion, all I'm going to need to do is the same kind of dimensional analysis that I've been doing all along. So 39.94 inches of mercury multiplied by inches of mercury need to go in the denominator. 29.92 inches of mercury for every 760 millimeters of mercury. Put that out there, and it equals so 39.94 multiplied by 760 divided by 29.92 to 3 significant figures, because I have 3 here in my 760. It would be 1,010 millimeters of mercury. In the second question, I'm asked to convert between millimeters of mercury and atmospheres. I know that there are 700 millimeters of mercury in 1 atmosphere, so my process is going to be pretty similar. 211 millimeters of mercury. Set up my dimensional analysis to do the unit conversion. Millimeters of mercury go in the denominator to cancel out. $211 divided by 760 to 3 significant figures, 0.278 atmospheres of pressure. So pressure conversions are really nothing different than what we've done in chapter 1. The only difference is that we now have new conversions to use. But the process is the same. Set up my conversion factor so that my units cancel, and therefore I am left with just the thing that I'm trying to find. All right, let's look at the gas laws themselves now. So Boyle's law. Boyle is Robert Boyle, English physicist, experimentally determined the relationship between pressure and volume at a constant temperature. And what he said is that the pressure and the volume of a gas are inversely related. That means that when the pressure increases, the volume decreases. And when the pressure decreases, the volume increases. That's what we mean by an inverse relationship. One goes up, the other one goes down. Now, mathematically speaking, we can express this with this equation. P1V1 is equal to P2V2. P1 would be the initial pressure. P2 would be the final pressure. V1 is equal to the initial volume. V2 is equal to the final volume. So if I have a question come up with those parameters, I just understand that when I see the ones refer to initial conditions, where we started. The twos refer to final conditions, where we end up. And so that way I shouldn't be able to get confused in terms of what numbers go in what places. The second gas law that we're going to uncover, Charles' law. Charles' law is associated with Jacques Charles, a French physicist. He just demonstrates the relationship between temperature and volume. And this one is a direct relationship. Temperature increases, volume increases. Temperature decreases, volume decreases as well. Now, notice the difference in the mathematics here. When they were inversely related, my ones were all multiplied together. My twos were all multiplied together. Notice here, we've got a direct relationship, and that direct relationship leads to division. Direct relationships lead to division. Inverse relationships lead to multiplication. Now, big side note here. These temperatures are absolute temperatures, which means they need to be in Kelvin, not Celsius. So convert all temperatures to Kelvin before solving. You have to do that. If you don't do that, you won't get the right answer. You'll end up getting something way off because you'll have accounted for a much bigger temperature effect than actually was there. Gay-Lussac's law, sometimes referred to as Amundsen's law. Joseph Gay-Lussac, again, a French physicist here, develops the relationship between pressure and temperature. And look at how the mathematical equation pulls out again here. This is a division. Division must mean a direct relationship. So this is a direct relationship. P increases, so does T. If P decreases, so does T. And once again, my temperatures have to be in Kelvin. I have to convert before I calculate. And remember, the relationship Kelvin is equal to Celsius plus 273.15. So that's the conversion that you have to make. Have to make that conversion before you calculate any changes using the Gay-Lussac or the Charles law. Now there's one more law that we want to talk about, and this involves the integration of something that we haven't talked about yet, and that's the integration of the number of moles. This is Avogadro's law. Now Avogadro is probably best known for his big number, 6.022 times 10 to the 23rd particles per mole. Well, one of the ways that he came up with that number was with his work through gases. And so the gas relationship that he establishes is that volume of gas and the amount of gas are directly related. And again, this should make sense. Anyone who's blown up a balloon, you blow up a balloon, as you add more gas into the balloon expands and expands and expands. So no shock at all that this is a direct relationship. And so as the number of gas molecules increase, the volume increases as well. And same thing in reverse. And once again, we see that the calculations here, our initial conditions were all divisions. And so the last point that we're going to make in this particular video is what are known as common reference points. And the most common reference point for a gas is something called standard temperature and pressure, STP. Standard temperature and pressure is a common condition. It's actually a condition that's related to Avogadro's law, because what Avogadro's law establishes, and this is again how he comes up to the number that he comes up to, but at these conditions, 1 atmosphere of pressure, 273 Kelvin, what we determine is that that is the standard temperature and pressure. That is the pressure that we compare all gases to each other using. And what's really interesting about this particular pressure and temperature condition is that if I have 1 mole of gas at STP, that gas should take up 22.4 liters of space. So 22.4 liters of space is equal to 1 mole. if we are at standard temperature and pressure. And that is one of the big takeaways from Avogadro's law, is that it established that that relationship existed regardless of what the gas was. So it didn't matter if it was sulfur dioxide or helium. If it was sulfur hexafluoride, one of the heaviest gases that we know of, or one of the lightest gases we know of in helium or hydrogen. If they're at STP, they take up the same amount of space, 22.4 liters. So what we'll be moving into in our next video, the Wednesday video, is we will be looking at how do we use these kinds of relationships to do some calculations quantitatively. And that'll wrap up the chapter for us. So thank you for watching, and I will see you next time.